This is our business analytics project, and we did it on Airbnb prices in Chicago.
So the question that we are proposing is, how do different seasons affect price fluctuations of Airbnb locations in Chicago, Illinois? The measures we used were independent variables, which included room type, reviews, overall satisfaction, and season, and then our dependent variable was price. We got our data from Townsley.net, and the main methods that we used were multiple linear regression and time series analysis. The other methods that we opted not to go with were simple linear regression and chi-squared testing. And then for our conclusion, based on our findings from this particular study, we can conclude that using a different level of significance and more advanced method would result in a more accurate result. So the main motivation for our business problem in question was to investigate price fluctuations of 50 Airbnb locations in Chicago throughout the whole of 2016 to see if they changed based on the season. This topic is important to college students because price is a deciding factor when looking for an Airbnb location. We chose Chicago specifically because it is very close to Iowa, with it being only a 3-hour drive. And then once more, our question is, how do different seasons affect price fluctuations of Airbnb locations in Chicago? So some assumptions about our data is that it's relevant enough, being that it's only from 2016, and that future fluctuations will therefore be similar. And then also, we had to take into account that price inflation was different 4 years ago. So for our data, we got it from Townsley.net, and that is a public website, so we thought that we had unlimited access, which gave us on average about 6,718 samples per month, and then in total that was 80,000 samples, and we ended up reducing it to the first 50 room IDs that repeated in all 12 months using the pivot table. So for our raw data, it contained room ID, host ID, room type, neighborhood, reviews, overall satisfaction, number accommodated, bedrooms, price, minimum night stay, latitude, longitude, and last modified. Ultimately, we ended up removing a few of these, which included host ID, last modified, longitude, and latitude because they were redundant. And then we also removed number accommodated, bedrooms, and minimum night stay because they had too much missing data across the samples that we selected.
We decided to use a multiple linear regression, being that it would be the best way to reveal if there's any correlation or relationship in the data. The dependent variable was price, and we had multiple independent variables being room type, reviews, overall satisfaction, and season. We had to test for multicollinearity to see if there were any correlations between the independent variables. We also had to use dummy variables to distinguish between the different seasons, summer, spring, fall, and winter, being that they are categorical variables. To distinguish if the room was a private room or not, we assigned a 1 to a private room and a 0 to a non-private room. We ran 5 regressions total, removing insignificant variables and adding in both t and reviews squared. We are able to use a time series analysis using the 12 months from 1 year to measure the price over time. We ruled out using a simple linear regression due to the fact that we had multiple independent variables and the significance was not high enough using one variable. We also ruled out using the chi-squared testing due to the fact that we had multiple independent variables and the test compares to categorical variables.
We did multiple regression to find the final regression equation. This can be interpreted as $155.49 decreased by $96.85 depending on whether it's a private room or not, decreased by 35 cents times the review scored, plus $0 times the review scored squared, plus 29 cents times the period it's in, plus 0 cents times t squared.
All right, for our statistical analysis, we have 3 assumptions. First is independence, second is normality, and the third is homoscedasticity. So for independence, basically we'll assume that each observation is not related to another. And then for normality, we will assume that if we were to put all of our observations into a histogram, it would not skew left or right. It would have a nice bell-shaped curve. And for homoscedasticity, we would basically assume that the quality of the variance is not following any sort of triangular pattern if we were to put it onto a scatter plot. These are the graphs for our residuals from our final regression. And as you can see, the normal probability plot is not normal, but because it's beyond the scope of this class, we will assume for our regression that it is and continue on with our regression analysis. For the private room residual plot, it's a bit skewed because the negative observations are a little bit closer to 0, and the positive tend to be farther away, meaning that the variance is a little bit skewed. And for the t-squared residual plot, we ran the regression multiple times trying to get the data points to show up with adjusting the x and y variables, but still we could only get a blank graph. So we will assume for that one as well. And as you can see, our T residuals, reviews, and our total residuals all together are not normal as well, but because that is beyond the scope of this class, we will continue on with our regression and move forward with our analysis. So in our testing for multilinearity, we set all of our independent variables in a chart versus each other, and then we use the Correll function to see whether or not each independent variable was related to each other and by how much. So as you can see, there's ones across here because summer should be directly correlated with summer because they are the same thing, and so on. So as a rule of thumb, none besides the ones that are directly correlated with each other because they're the same thing, are above 0.7. And because of that, we can go ahead and move on and confirm that none of these will be a problem with moving forward, and we can assume that none are multicollinear. For our first regression, we got an R-square of 0.373541, and this can be interpreted as 37.35% of our variance in our data can be explained, and our significance F is less than our alpha, which is 0.05, so we can check that off and move on and now look at our p-values. So all of the p-values except for spring, overall satisfaction, and T were less than 0.05. And as you can see for the p-values that are greater, if you look at the confidence interval, 0 is contained in these ones, so we cannot confirm that it is significantly different from 0 for those 3 independent variables. Therefore, we cannot reject the null hypothesis for those, and we will have to continue by removing one at a time from each regression until all of the p-values are less than 0.05. So we will start with overall satisfaction and remove that because it is the highest p-value of all the other ones. On to our second regression. Our R-squared increased, so now it is 40.26% of the variance in our data can be explained. And our significance F is still lower than 0.05, so we're good there. And now we only have spring with a p-value of greater than our significance level of 0.05. So next we will be removing spring and running the regression again. For our third regression, we have 40.09% of data variance explained. And then for our significance F, still, as you can see, is less than alpha. And now with removing spring, we just have summer that is a larger p-value. So we will be removing that next. And on to our fourth regression, 39.82% is explained, significance F is good, and now fall is the p-value that is too large. So for our fifth and final regression, we have a final R-square of 0.396, so 39.6% of variance can be explained by our data. And the significance F-score is less than our significance level of 0.05, and all of the p-values are less than 0.05 as well. So we will use the coefficients of these independent variables to formulate our final model and create our equation. And for our time series data, we used the month versus the price, and then we did forecasting with naive, average forecasting, 3-month moving average, and exponential smoothing. So from this data, you can see that 4.73, 5.48, 5.04, and 10.5 are the final mean squared errors. And so the best model to use for time series in this case for this data would be actually the naive forecast, because it has the lowest mean squared error.
In conclusion, others in the analytics profession may use other levels of significance, but for the scope of this class, we used 0.05. Some weaknesses are that to have a more accurate regression equation, we would have to do more sophisticated methods that are beyond the scope of this class and like what we learned. So if others wanted to use this data in the future, they would have to use other methods. Some things that we were surprised about that we didn't expect at the beginning was that the graphs of the residuals weren't normal, and so our normal multiple regression equation isn't completely accurate.